now we're going to look at calculating the voltage profile for an infinitely long line of charge. So we have a wire that we have charged up, and we want to know the voltage profile for this infinite line charge. Well, what I have shown here is the calculation using Gauss's law to get the electric field as a function of R. So we're going to need to do that first. So anytime we can use Gauss's law to calculate an electric field, the bottom line is use it. We use Gauss's law to get the electric field, even if it's a voltage profile that we're ultimately interested in. So what I would like you to do is pause the video here, copy this down, take a look at the Gauss's law calculation that is here. When you unpause, I will come back and give you a very brief explanation to hopefully jog your memory if you needed it, and then we'll move on to the voltage profile. So pause the video here. Okay, hopefully this calculation looks familiar to us. We use the Gaussian surface of this cylinder coaxial to our wire. It's a finite cylinder, and that's okay. We'll see why in a moment. We have a Gaussian surface with two end caps, an n hat over here, an n hat over here, and then an n hat on the shell. The electric field from our wire points radially out. It's like the spokes of the spokes on a wheel, radially out, and because of that, we get 90 degrees for our two end caps. So we get cosine of 90 degrees is 0. So that is why we lose our end cap calculations. We have the electric field in the same direction as the n hat, so we get cosine of 0 for the shell, and that's why we keep the shell. We would expect the electric field to be constant anywhere on the surface of the shell by symmetry, so that comes out by symmetry, of course, and then we are in business. The electric field is constant on the shell. The integral of dA is A. The area of the shell is 2 pi r times the script L. The Q enclosed is only enclosed in the Gaussian surface, and as it shows over here, we're going to use our density calculation, charge, which is coulombs per meter, gives us our line density. We then solve for Q enclosed is lambda L. We get the lambda L in there. We lose the L's, and voila, we get our electric field as a function of R. Now we are going to use this electric field expression to generate the voltage profile. So let's see how that is done. So here we are simply going to take our electric field value that we just calculated using Gauss's law, and we are going to substitute it into our equation delta V equals negative the integral E dot ds, and it is always important to note that, let me explode this, we have to integrate inward. And please make a note here. This is the one case where when we integrate inward, we will not be going in from infinity. So put in here, but not from infinity, and we'll see why not from infinity in a moment. Well, let's just finish our calculation. So we have R final, R initial, and R initial will not be infinity. We'll see why in a moment. If we take our electric field and plug it in here, we can take the lambda on 2 pi epsilon naught and bring it out because it's constant. So we're left with the integral of 1 on r dr, which is, of course, the natural log of r. And we're going to integrate it from initial to final. And R initial will not be infinity in this case. And again, let's see why by finishing up our calculation. Well, when we do final minus initial, we have final, right, minus initial, natural log. Well, we're going to carry the extra negative through, and then do natural log of A minus natural log of B is natural log of A on B to get our voltage profile answer. So this is our voltage equation, and we would have the delta V, right? So it would equal delta V. That's the delta V out here. So this together equals delta V, but delta V is final, right? Final minus initial. And please make a note that if you go back and look at your notes, we need to look at this. So what we are going to do is let the voltage equal 0 at R initial. So in other words, when R equals R initial, which will be problem specific. So anytime you look at a problem, you're going to have to see, well, where are they starting? Where are they ending the problem? Make sure that the R initial equals 0, or the R initial value will give you the voltage equaling 0. And that's what we want. We want the voltage value to be 0 at our reference, and that's exactly what happens. So at R final, when R final equals R initial, we get the natural log of 1, which equals 0. See, it's the natural log that's our problem. Natural log doesn't go to 0 as you go to infinity. If you want to show that to yourself, take the natural log of 1,000,000. So that's out there. It's not infinity, but that's far. The natural log of 1,000,000 is 13.8. The natural log of 10,000,000, we're getting closer to infinity, is 16.1. So 13.8 and 16.1 is actually getting bigger. It's not going to 0. So it's a little goofy in terms of thinking about functions where normally our intuition might be that everything should go to a 0 in infinity, but the natural log function does not. And this will make more sense as we go along and look at problems and solve them numerically.